Welcome back for day 8. We're right into it today with Playground. We teleported junction boxes. Which junction boxes connect so that electricity can reach every junction box? They even have a list of all the junction boxes positions in 3D space. Okay, 3D space problem. We've got, I don't know, an IVEC 3, we'll call this, on each line. Each position is XYZ. First junction box is yeah. Focus on connecting pairs of junction boxes that are as close together as possible according to straight line distance. So, like vec distance vec, which is just subtraction of magnitude. But GLAM here would let us do that with dot distance, which I think is better to read in code. So we'll do that. My guess is that doing this on the full input is going to be prohibitively expensive, but we'll see. In this example, the two that are closest together are these two. They become part of a circuit. So they become a circuit, and the remaining 18 are in their own individual circuits. Oh, this is going to be a lot of rules, isn't it? Okay. Now the two junction boxes which are closest together but aren't already directly connected are these two. After connecting them, 168,812 is already connected to another junction box. There's now a single circuit which contains 3 junction boxes and an additional 17. I feel like my question immediately here is like, can you connect from middle to middle? Right? We have 3 now. Can we connect? Or does it have to be like one line? Important note, 2 junction boxes. These 2 connected. Now we have a 3, a 2, and 15 individuals. The next 2 are... I feel like this is sorting everything by distance and then iterating over them. Because otherwise, why would you be iterating over junction boxes that are already in the same circuit? Unless you were doing something like calculating all the distances and then iterating over them by distance. After making the 10 shortest connections, there are 11 circuits. One circuit contains 5 boxes, 1, 4, 1, 2, and 7 singles. Multiplying together the sizes of the 3 largest circuits, so 5, 4, and a 2, produces 40. Your list contains many boxes. Connect together the 1,000 pairs of junction boxes which are closest together. Afterwards, what do you get if you multiply together the sizes of the 3 largest circuits? So our test input is this, day 8. I am just going to go right in here and make sure that we have GLAM available because that seems to make the most sense to me from like a readability perspective, right? Like we could keep all of these in tuples. They're all ordered. It's all XYZ. But if we ever have to pull those values out, I really want to be able to pull out like .x, .y, .z. And it's really no overhead to create these vecs. So I think we'll do that. This is our input. I think we immediately parse these into a vec of IVEC3s. What's our number here? We need 40. And we've got a couple of sub-steps that we could also test, but let's see. Also, we have different configuration for the input. I am going to start with just testing, and then we'll split out a function later to like be able to pass in this configuration to connect 1,000, or I think this one connects 10 is our test 10. This is 20 boxes, the 10 shortest connections. So I think I'll just do a non-parser. I can already think about how to do this very straightforwardly. We'll need an IVEC3. I guess we could do a UVEC3. Let's take a look at the input. I think this is, we've got 5-digit numbers here. So I guess we could do UVEC, but so we've got a separated list 1 by line ending. This is our dot lines equivalent. And I'm actually going to do, I think, a tuple here. I feel like the only question I have here is like, I think UVEC might be better. I like working with IVECs because it means we can subtract them easier. But if we're just doing dot distance, do we really need that? Right? We've got a bunch of different types for all of the different integer types and all the different float types and stuff. The float types are typically what's used in like Bevy or a game engine or something like that for the F32s. And then these are all our integer types, which are kind of more in line with usage for Advent of Code because they're usually integer-based problems. I guess let's just parse I32s. I started with I32s. It's not a big deal. We can always change it. Like changing that is not going to be difficult. and I guess it doesn't really matter. So we can get our separated list, we can map over that separated list and pass the slice into an IVEC3, which means that we should end up with input and positions and parse. And if we cargo test, not day 6, we'll do day 8, part 1. This will fail. We should get all of the inputs here. Let's see. Our last number should be 425, 690, 689. So we have all of our IVEC3s here. Make sure we have the first number as well, 162, 817, 812. That's all fine. So just a very quick parser. And then we need what? The Cartesian product, which is basically every number with every other, which should be able to give us a tuple here, right? We IVEC3, IVEC3. We just do a.distance b. If you want to look at the implementation of distance, you can go to the GLAM. I guess there's a issue with that. Oh, cool. Manhattan distance is in here. That's fun. We want straight line distance. We don't want Manhattan distance. So if we look at like what Manhattan distance is, we've got green line, blue line, red, and yellow. So if we want straight line distance, the green line is going to be the shortest. Well, in any case, the VEC3 itself has what I wanted to show. And if you look at the source for what a distance is a minus b dot length. They specifically say they want the straight line distance. So I think we have to use F32s to get the right distance values, and I'm assuming that's going to be important. So we can just easily convert these to VEC3s to get that distance. So we have our 2 integers now and a float distance. And we want to sort it by that distance. Sorted by key comes from itertools. There's something wrong here. Right, ord is not implemented for F32. I always forget that Bevy provides float ord. So this is what I'm used to just having available all the time. And there are some caveats here, but I don't think it matters to us. So unfortunately, all that really means for us is that we can't use sorted by key there, and we have to do our own comparisons for these floats. In this case, I'm kind of encoding the fact that I'm expecting 0 nans. So our problem should be well formed. It's advent of code. So I'm not really expecting to see any problems here. So if we just like debug AB distance here, we should be able to see a bunch of distances. I'll probably do info here instead, actually. Right, A and B are still these IVECs, so I'm going to try to treat the IVECs as kind of our identifiers, which is why I'm keeping them around. And then we end up with this list. So 162, 817, 812. I think the one problem here with Cartesian product is that these are going to compare to themselves. So we're going to end up skipping a whole bunch of these. So we could probably actually even throw this up into filter map here and encode this as if A equals B, none, otherwise do our calculations. And then these should just not exist anymore. So now we have 162, 817, 812, and 425. Our test input, 162, 425. That looks right. And then it wants us to do... This actually gives us the same thing in reverse order, which is also weird. I think we actually just want the combinations. We don't want the Cartesian product. So if we combinations, we end up with a VEC of these things. I actually want, I think, tuple combinations to keep our... One of the things I really like keeping is this encoding of how many we're expecting to deal with. If we do combinations 2, we end up with that VEC. And that's fine if we're passing something as a slice or doing some kind of operation that doesn't care how long it is. But in this case, we're always intending to have 2 no matter what. So when working with things like this, I like personally doing either tuple or const generic based iterators. Now, tuple combinations has some issues with longer combinations. So like it's implemented for homogeneous tuples of self item with size up to 12, right? This is kind of a restriction that's pretty common in the Rust ecosystem right now. And there are some newer APIs that are on nightly that do use const generics to be able to give you, for example, a slice of 2 when you're iterating over, but they are nightly only. So that's kind of why I'm avoiding them and choosing to use itertools and work with stable. So this is 162, 816, that looks right, 425, 162, 431, 906, 805, 431, 425. These all look correct at this point. So I'm going to assume that without checking all the rest of them, that this is the correct list now. We actually don't need this A-B check anymore, I don't think. Right? We never get the same element paired with itself. So we never get a distance of 0, so we don't have to do that filter map anymore. Then we've got it sorted. So we've got all of our positions sorted by distance. We need to iterate over these. I guess we have a couple of options here. There's nothing that is, how should I say this? There's nothing that says what order we need to connect the cables in, as far as I can tell. I'm assuming that's a part 2 thing. So all we really have is junction boxes. We've got our one iteration happening. And I can think of kind of 2 ways to handle this. We need to do 10 connections, right? So we could either maintain some state about how many connections we've inserted, right? This connections thing here would have to be like a vec of vecs of ivec3s. So we've got the outer vec, which is all the connections. We've got the inner vec, which is each cluster. We're going to iter mute, find a cluster that fits. If both items aren't in that cluster, insert one. And I don't think the actual direction of the connections matters for us right now. So I'm not going to do like a graph or something like that until we actually require it. I think this is fine. I'm going to keep an extra variable here. And the question I have is, do we need to do 10 connections after making the 10 shortest connections? So there is no guarantee about what number that vec of vecs is going to be, right? No guarantees about how many groups they're going to be. No guarantees about how many items are going to be in those groups. So we can't like flatten that or length it or do any kind of check like that in the vec. If we have a valid connection to make that isn't filtered, then this number bumps up by 1. We do a check on this. So if connections 10 break, otherwise have our stuff, and then connections dot iter dot find A. I guess that's A or B, right? If either of these are in a cluster, right? Cluster contains A or cluster dot contains B. I guess we could iter mute this if we really wanted to. The one thing we can't do iter mute to is iter mute to something that isn't labeled as such. So if let sum cluster equals connections, I think my semicolon is missing here. What is, oh, it's the return value. Okay, this is my syntax being wrong. So what we have here is a failure to communicate. If we have a cluster, then this will be immutable access to that cluster. This find doesn't tell us which one is already in the cluster. We do know one is in though. So we could do a match here. I think we want that cluster item, right? And we also want the data that we're using to calculate this find. So we could do a find map. This is going to have to be a tuple. So then we end up with basically doing the calculations. So it contains A, contains B. We could early terminate here. Not too concerned about it. Not at the moment anyway. So we end up with all of our connection clusters. We're iterating mutably over them. We're finding the cluster that contains one or both of these. And then I've stuck this in like a secondary thing here. This is not actually cluster, right? This is result, which is cluster, and then a couple of Booleans. And I'm choosing to be complete here because what I want to do is ensure through the compiler that I've covered my cases. In this case, though, we just filtered for a truth, so this should never happen. For true, we also just do nothing. And then for these, we're going to do individual insertions. So cluster dot push B. And I guess this is going to be like a clone, right? Or a copy or whatever. So this is just the way that it's kind of like coming out in my head. But there might be a better way to write this later. What are we calling these? These are cluster contains one of the junction boxes, and then no cluster contains junction boxes, right? And if nothing contains a cluster junction box, then we want connections dot push vec with A and B in it, both as values, and then we continue. So theoretically, we want to be bumping this connections number as well. So if we're going to push in, we're going to add 1, and then we have hopefully our connections. So here's our connections. I don't have my tracing subscriber set up to do new lines, which you absolutely can do, but isn't really that worth it for me right now. So I'm just going to switch to debug for a second, go 1, 2, 3, 4, 5, 6. That seems like too many. What are the numbers we're supposed to have? Multiplying the sizes of the 3 largest circuits, 5, 4, and 2. One circuit contains 4. Did I add the wrong ones in? Am I like pushing extras in? Let's see. Do we have any duplicates? This has 7 items, which is wrong. So something's wrong here. What is wrong is the question. This unfortunately is given in prose, which is really annoying to translate. And it doesn't give us the actual output, so we're just gonna have to work through it, I guess. This is 4. This is 3. This is 4. And then we've got 2 groups of 2. So we're trying to find the first one, right? I guess technically speaking, these could merge, but that would create bigger groups, not smaller groups. Okay, I'm gonna need to copy and paste this in. This is just not my favorite. So these are in one group. Let's log out the remaining number as well. Now this should stop at 10, so it should be 10. But maybe they didn't mean 10. Maybe they just mean process 10. So I should check that first. So if we just bump it up here and we do 10, do we end up with the right number? This is then 4, 4, 2, 2, 2, when it's supposed to be 5, 4, 2, 2, 2. And letting it go for that extra iteration does give us 1, 2, 3, 4, 5, 4. But then we have 3 2s, which is weird. So I think something's wrong in the logic, or in my definition of what distance is, or something like that. It's unfortunate that they don't give anything about what distance actually is here. I did make the assumption that, like, they say straight line. But let's see. Let's go back to, I guess, the way I had it before and try to figure out if this is even the right set of stuff. Now the 2 connected closest are these 2. So this joins that group. This is the next one. This is the other thing we can do. We can actually set up our program to output this for each loop, which will probably be good to know. These 2 are already in the same circuit, and the process continues for a while. Okay, cool. So like 162, 425, 431, all correct, right? And then 906, 805, correct. And then the rest is just kind of like draw the rest of the owl, good luck. What are we logging out right now? Each one that we're processing, but we could log out connections instead to see how this grows. So we start with a cluster of 162 and 425. We start with a cluster of these 3 for the next one. Next cluster is 906, 805. Next 2 junction boxes are 431 and 425, which are already in, so we end up with the same connections list. Well, that's really unfortunate. Where's our 10? After making the 10 shortest connections. So it's just total 10? Because we don't make connections if connections already exist, right? I think this is what it wants. And I think that we are supposed to throw this every single time. So it's like take 10, not, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 1, 2. The only thing that's bothering me here is there's an extra 2. Like that gets our answer correct for the test, but then why do we have an extra 2? Right? The other thing is that we don't actually need to keep count if that's the case, because we can just take 10, which does the same thing. But that is not 10 connections. That's not making 10 connections. That is just taking 10 connections that should exist. So I missed something in the question then, or my distance calculation is wrong. This test description unfortunately does not describe enough data for me to test anymore.
So I actually have no idea what the list is supposed to look like. All I know is that this is supposed to be wrong, right? We're supposed to have a 5, a 4, and 2 2s. I guess we're supposed to be taking circuits out if they're in this at all, is the thing, right? So like if is this last one supposed to be merged into the first one, actually, now that I think about it? 819, 941. Looking for 346. Actually, there's a 906, 805, 819, 941, 52, 117, 862, 984. This one. This one has to be merged into the other one, is what has to happen. That's where the problem is. So what we end up having is, if this is actually included in multiple, then we need to merge those, right? If it's a connection, there can be one connection between two groups, and those two groups have to merge if so. So instead of find map, this is going to be filter, which is not good because we're doing an intermute, and filter returns multiple results. I don't think we want to make this mutable at the moment. And I think we're going to filter map here. And I think we have to collect. That feels really awkward. All right, because we kind of want position, but we don't really want position. We want positions, which we could enumerate filter. itertools does have positions, so we probably don't want to map this anymore. And I'm just going to return this Boolean, right? Because this is going to give us back potentially multiple indices now. If I can remember how to write a turbofish. So we get a vec of usize. So let's move this up. Let matches equals this, right? So we should be able to take that matches, turn it into a slice, match on the number of potential values. So we're either going to have no matches, one match, or two matches. If we have more than two matches, then we have a problem, because that means that we inserted multiple independent pairs of two that already had matches existing. So we've messed something up. So if this happens, we panic. If there's nothing, then we push our two in. If there's one, we need to pull this shenanigan that we already wrote. And we need to do this calculation again, unfortunately, I think, because we have to know which one actually is contained. I'm going to spell my unwrap correctly, and we're going to get a mutable reference to that vec. We are then going to match on the tuple that is contains for both of these. And the things that we need to do are like this. So if one, then push B. If the other, we could do this in two ifs as well instead, which might be better, except for the fact that we have to do nothing if they're both true. So if there is no match, then we push. If there's one match, we figure out which one is involved, and then we push. If they're both involved, then we do nothing. And if we have two of them, then really what we need to do is grab these two. We'll do into iter for both of them because we own them now. I'll register them as unique, right? Collect into a vec of ivec3s, push new cluster in. And now, if we get rid of the code we had here, take 10 is going to be wrong, I think. But let's test it. This is 5, 2, 2, 4. 5, 4, 2, 2. That's actually right. So I think it is just process 10. And it is not actually as complicated as I thought it was going to be. We don't actually need the distance there, and we don't need these num connections. I thought we were going to have to track the number of connections that we were actually making, but this is just process all of the connections. It's not make 10 connections. So this is connections dot sort by a dot length, b dot length. And in this case, that is going to be reversed. So we actually want BA. So we have 5, 4, 2, 2. Is that correct? 5, 4, 2, 2. I feel like there was supposed to be a 3. 5, 4 in one of the circuits that produces 2. So we can do connections dot map to the lengths, take 3. The only concern I have here is that if this number is greater than the number we have to fill it with ones. And I have no idea what the actual input is going to do. So let's do a quick take 30 here. I guess dot product. If we're doing dot product on these, then multiplying by 1 won't matter. So really, what's the behavior if we take too many? If we take too many, then it is, 5 times 4 times 2 times 2? 20 times 2 times 2? So actually, it doesn't matter. And in this case, we take 3, and that's just our answer. Because multiplying by 1 won't change anything anyway. So we don't even need to worry about it. So this test should pass now. And technically, that runs part 1. These numbers need to change, though, is the other thing. So we could rip this whole thing out, throw it into a function that is, what are we going to call this function? I'm going to call it groups because I don't have a better name for it at the moment. And we need to accept configuration that is, what are we calling these? Pairs. We need to connect 1,000 pairs and then the 3 largest circuits. And then this is num pairs. So we need positions, which is the vec of vec. No, it's the vec of ivec3s. We need num largest as a usize and num pairs as a usize. And this is groups. I guess 10 is always the case, or 3 is always the case, but we'll call this output and say that we return a usize here and pass in positions. So we test and this still works. And then I'm just going to bump the number up and run. Removal index is 137, should be less than length. Ooh, that's annoying. I know what that problem is. We're doing 2 removes. And remove changes the index, right? Removes and returns the element at position index within the vector, shifting all elements after it to the left. So if we remove the index that is before it, then it will shift to the left. So we have 2 options here. And really what I think I'm going to do for these removes is actually do a min and a max. So because remove shifts everything, I think everything to the right to the left, right? Is the right way to frame that? Shifting all elements after it to the left. So it shifts everything to the right to the left. If we do the rightmost one first, then our leftmost index is still correct. And that's our gold star for part 1. Huzzah! So the L's were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they're all in one large circuit. Continuing the above example, the first connection which causes all of the junction boxes to form a single circuit is between the junction boxes. The elves need to know how far these junction boxes are from the wall so they can pick the right extension cable. Continue connecting the closest unconnected pairs until they're all in the same circuit. What do you get if you multiply together the x coordinates of the last 2 junction boxes? That seems pretty straightforward comparatively. So our answer here is going to be 25,272 for our test. And then I think we get to pull this back, right? We just need to know, what the last connection or the connection that creates a single loop. So they're all going to end up merging in just like we have it. And then we just need to detect if we have created a single after we've done a merge. So take is no longer in play for part 2. And when we do a merge, we only need to do this logic if, well, we haven't done any unique list, right? If the new cluster includes all positions, then we return a.x times b.x, which I've shadowed here. So this a and this b are what we actually need. And I shadowed the variable names here. So actually what I'm going to do here is B group, A group. And then this is ivex, right? So actually this needs to be like as usize here. And then we just need the list of all positions. And this stuff doesn't matter. And if we ever reach the end, then we have to panic in the current setup. which is really actually better represented as a result, right? So result usize. And our return here is going to be okay. And this is actually going to be, I guess we don't have an error type here yet. So error uncalculatable. We're just going to make this like a string error. No real reason for us to do too much work here. We could use Miet here, actually. Right, Miet string. We don't, in general, care about processing this error. Found unit. Do we have a return in here? Oh, found unit because of this. So I'll just use the Miet macro to construct a string like error. It's a little bit more than an error. Miet includes a bunch of reporting, which is cool. And then we actually get the opportunity to do the same here, right? Encounter too many matching indices. Now we could add more data here, but we're actually never going to hit this and never going to see that. I just wrote it for kicks. So groups is now an unwrap here. We'll still get that usize. We do have to pass in all positions. Actually, positions is all positions, isn't it? So it's actually just positions.length. And if we test part 2, I get an error uncalculatable. We never hit this, which is interesting. Oh, because positions... No, positions is the full list. So what's wrong here? Let me info connections here. And we end up with connections that, as far as I can tell, is everything. So what I've done here is just include a little bit more info logging. And this is con length 1. That's what we need, though. So I'm going to label this as connections. So they're both the same length. I guess that means that the merging isn't what creates the end. So really, I'm surprised this never hits. But I guess that's not the issue. So if connections.length is 1 and connection0.length equals positions.length, then we return. But where does this get caught is the question. I guess it could be technically anywhere. We need A and B, so it has to happen in some loop, right? If we do an insertion, then we have to do the check. If we do a single push, we have to do the check. If we do a merge, we have to do the check. And in all other cases, we don't. So technically speaking, there are a limited set of places that we need to do the check. And if I put them all in at those places, then we pass our test. And if I run the part 2 actual, we get our gold star. Sweet. So we are slow today. We have 20 milliseconds and 25 milliseconds. I feel like the way that I would think of in general to do this would actually be pulling in petgraph and doing real graph operations and doing probably an iteration, I guess, over the graph to see if everything is connected. And then we would get rid of a whole ton of these checks because we could just constantly do, or really what we could do is just constantly insert the edges. Insert edge, check. Insert edge, check. Oh, petgraph has a logo now? When did petgraph get a logo? That's so cute. But petgraph is a graph library. We haven't really had an opportunity to use it. I would really like to use it. I like showing it off sometimes. We didn't particularly need it today, but I might do a refactor that uses a graph actually instead of this amalgamation of vex. Typically, these are, or rather, typically petgraph is used for either pathfinding algorithms or the pathfinding crate is. And sometimes it's the only solution comparatively. And then we could do something like run connected components, right? Connected components, as long as we have one, yada, yada, like that kind of thing. In this case, we do end up with everything in one at the end of the day. So I think the fact that this would return like potentially multiple is not a problem. But yeah, just a brief look into something that is potentially better in terms of data structure application. We don't actually use any of the edges. We just detect here whether they're connected or not. I do think doing the tuple combinations is fine. Calculating the distances is fine. Rust iterators are lazy. So unfortunately, we do have to do this sorted by, which collects all of them.
which means that we're basically allocating a giant vec up front. And then we have the issue of each index could theoretically be in up to 2 groups. So we have to iterate over the connections in some way. We then take that slice and we push into the connections with a new vec, or we run some more logic. I think that the merging overall is probably the most expensive piece. This vec is probably also growing past its allocation. But yeah, I don't know. 20 milliseconds is probably pretty slow for adjunctive code. It's fine for actually computing the problem, so I'm going to probably leave it like this. Part 2, I'm going to get rid of these little extra arguments that we're no longer using for the part 2 solution. It was nice that our part 1 basically translated directly into part 2. So if we were writing for part 2, maybe we could have written it more efficiently to start with. But yeah, I think that's it for today. Hope you had fun today, and I will see you tomorrow for the next one.